This video is discussing a specific type of rotational motion called uniform circular motion. Uniform circular motion refers to an object that is moving in a circle at a constant angular speed. So the question is, does an object in uniform circular motion have an acceleration? To help us answer this question, let's look at this little simulation. Here's an object moving in a circle at a constant speed. The green vector represents its velocity vector. Is its velocity vector the same at all times? If you answered no, you're correct. It may have the same length at all times, but it's not pointing in the same direction at all times. That means our object is accelerating. Just because something has the same speed does not mean that it does not have an acceleration. We have a specific name for this type of acceleration. It's called centripetal acceleration. Centripetal acceleration comes from a Latin word that means center seeking. That helps us know a little bit about its direction. Let's take a look at this again. This object is constantly moving in a circle, and its acceleration cannot have a component parallel to the velocity, or else it would end up accelerating. It would end up speeding up. So instead, the acceleration has to be perpendicular to the velocity. So you'll notice this blue vector here, which represents the centripetal acceleration. Does it have a common direction? Well, its direction is constantly changing, but it's always pointing toward the center of the circle. And that's what the word centripetal means. It means center seeking, pointing toward the center at all times. We have a special equation for this type of acceleration as well. Centripetal acceleration is equal to the tangential velocity squared divided by the radius. Well, we know tangential velocity is equal to angular velocity times radius. So I have angular velocity squared times radius squared divided by radius. So really, we have two equations we could use for centripetal acceleration. There's our first one, but we could also use angular speed squared times radius. One last important fact. While I've been talking about this acceleration in terms of uniform circular motion, an object does not need to be in uniform circular motion to have a centripetal acceleration. Anything that moves in a circle has a centripetal acceleration. Okay, let's take a look at an example problem that uses this equation. In this problem, we're talking about the centripetal acceleration due to Earth's rotation. We're talking about its axis of a man that's standing at the equator and a man that's standing at the North Pole. In these problems, it's much easier, in my opinion, to use the equation that centripetal acceleration is angular speed squared times radius, because I think it's much easier to come up with the angular speed. We're talking about due to Earth's rotation about its own axis. So as we learned in class, that means that it's just moving in a circle, and so the axis of rotation goes through the Earth. That means that the Earth makes one rotation, or one revolution, which is 2 pi radians, in a total of 24 hours. Well, we're not allowed to put hours in there. We need seconds. In one day, there are 86,400 seconds. Those two values will give me my angular speed of the Earth. Then I need to multiply by the radius. Well, if we have a man standing at the equator, that means the radius of his motion is equal to the radius of the Earth. That's a number that would be given to you. It's also a number you can find in the back of your textbook. That number is 6.38 times 10 to the 6th meters. If I multiply all of that out, I find that the centripetal acceleration of this man is 0.0337 meters per second squared. So this is for a man standing on the equator. What about for a man standing at the North Pole? Well, we learned that any 2 points on a rotating object have the same angular speed, so omega doesn't change. What about the radius? This can be a little bit deceiving. Radius, in this case, is the distance between the object and the axis of rotation, not automatically the radius of the Earth. So if a man is standing at the North Pole, what is this distance from the axis of rotation? Hopefully you said 0, because he's standing on the axis of rotation. That means that his centripetal acceleration is also 0. Let's take a look at another problem. This problem talks about giant rotating cylinders placed in space to be used as space colonies. It wants to know what angular speed this cylinder should have so that its centripetal acceleration is the same as the free fall acceleration on Earth. In other words, we're trying to find what angular speed you need for a centripetal acceleration to equal 9.8 meters per second squared. Well, let's think about exactly what this would look like, because this sounds kind of funny. Here's what they're talking about. They're talking about these giant rotating cylinders where people would live on the outside of them. Now, of course, my scale is going to be off here. It's very hard to draw so small. But there are some, let's say that there are some trees and houses on the outside. And there would be some on the other side as well. So how fast does this have to rotate? Well, let's see. It tells me that it would be 10,000 meters long and 5,000 meters in diameter. So this distance is 10,000 meters. And this here is 5,000 meters. I know I want centripetal acceleration to be 9.8 meters per second squared. Because it asked me what angular speed, I'm going to use the equation that centripetal acceleration is angular speed squared divided by times radius. That means that the angular speed is the square root of centripetal acceleration divided by radius. So that means we have the square root of 9.8 meters per second squared divided by the radius, which is not 5,000 meters, that's the diameter. We need half of that, or 2,500 meters. Plug all that into your calculator, and you find that it's a pretty small angular speed, 0.0626 radians per second. So it wouldn't have to rotate very fast because it's very, very large. This last problem, example number 11, is again one I'd like you to try on your own. So pause this video, try the problem, and then just bring the problem to class with you tomorrow. I will have answers in class tomorrow.